Hello, we are group number 1, confirmed by Daniel Morantes, David Ramos, and me, Sara Aguilar. Today we present our report regarding the fifth laboratory practice, diffusivity of a mosquito repellent. Here we can observe the table of contents about what we'll be discussing in this video.
Before knowing the results, it is necessary to know certain basic concepts that were necessary to achieve the objective of the practice, which is to develop a protocol to determine the effect of temperature on the diffusivity of a mosquito repellent. So first, what is a mosquito repellent? Mosquito repellents are volatile substances that, when applied to the skin, repel mosquitoes in opposite directions to their origin, thus preventing them from attacking the skin and causing bites. The importance of its use lies in the fact that it prevents or reduces the transmission of diseases transferred through mosquito bites such as malaria, dengue, chikungunya, among others. However, to know about its effectivity, it is necessary to know about its diffusion coefficient. The diffusion coefficient represents the ease with which a solid diffuses or moves in a given solvent. It depends on the temperature, the size and structure of the solute, and the viscosity, among others. The temperature of the liquid is crucial because at a low boiling point, the vapor pressure is lower, making the use of the repellent less effective. On the other hand, at lower the boiling point as the greater its effectiveness is.
Well, now for the methodology, what we did first was to heat the water and mark the beakers. Well, here it was a little bit difficult to reach the established temperatures that we have first, so we did it for 10, 40, 60, and 80 degrees. Well, the idea was because it was a little bit difficult to reach the 90 degrees temperature with the water. The second step was to add 30 milliliters of water to each beaker and define the distance. Well, the distance is just the length that we're going to consider the diffusion. And the third step was to add the liquid dye to the mosquito repellent. In our case, we use no Piquex as our mosquito repellent. The fourth step was to take 3 milliliters of the mosquito repellent and add it to each of the beaker that have the water in the with the different temperatures. The fifth step was to took some samples of the solution every minute for 4 minutes. Well, every minute the drops of the repellent is going to have like a different organization in the solution, so the sample is going to be different every minute. And the last step was to do the concentration analysis of each samples using the UVBIS to obtain the wavelength uh, against the absorbance of each sample. And that's all for the methodology. Now for the results, we have here first the graphs of the absorbance versus the wavelength. Well, we have here the 4 samples and the water at 10 degrees. Well, we can see that the graphs are quite similar. They have just like a little bit difference in like 16 nanometers because the last curve is like the only difference between the graph. And we can also see the highest point of absorption is in around 150 and 60 nanometers. We find that highest point later. Now for 40 degrees, that was our second temperature. While the graphs are also the same, and the highest point is also the same as the other ones. It's the same case for the 60 degrees, and also the same for 80 degrees. We have here also that the only difference is in the last curve. That for example, here in 2 minutes, the last one is a little bit sharp in exactly 60 nanometers, and in the other ones are like a little bit softer. So this is the only difference that we can find in these graphs. Well, we have here some important additional data that we obtained from the previous graphs. So first, we obtained the value from the maximum absorbance, and it was 10. And the wavelength of this maximum absorbance, it was 564.9 nanometers. Well, now for the Beer-Lambert equation, we have that the L is 1 centimeter. We have that the epsilon is 0.02 liters per mole times centimeter. For 500 nanometers, we obtain this value on the literature, and it is around the wavelength that we obtain because we cannot find an exact value of epsilon at the wavelength that we have of the maximum absorbance. And with the approximation of the short equation, we have here the distance that we define later. Sorry, before in the methodology that it was 2.7 centimeters, and our first temperature, our initial temperature, that is 25 centi-degrees. Well, in our note, we said that the concentration is the same for all the temperatures because of A. Well, in all the graphs, in all the temperatures, and all the times, we have the same maximum absorbance, and it's always 10, and it's always in the same wavelength. So that's the reason why we don't present a graph of diffusion coefficient versus concentration, because the concentration is always the same. In this graph, we can see the behavior of the diffusive coefficient versus the temperature in the different times. So we can see that there is a trend that with throughout the increasing of the temperature, the diffusive coefficient is always decreasing, and it is also decreasing throughout the pass of time, because the highest one is the one for 1 minute, and the lowest is the one for 4 minutes.
So we see that at minute 1, the diffusive coefficients decreases across the temperature. At 10 Celsius degrees, the diffusivity in centimeters squares per second, it's 0.125. In 40 Celsius degrees is 0.118. In 60 Celsius degrees is 0.114, and in 80 Celsius degrees is 0.109 centimeters squares per second. But we see that in every equation, diffusivity is directly proportional at temperature. We see Chapman and Scott that it's in a factor of 3 of cube to root squared. And in Soret, the higher is the delta of the temperature, the higher is also the diffusivity. Well, this is because of the Brownian motion. Because the greater the diffusivity, the molecule expand more and more on the water or in the medium of their expanding. And with the time, the less space they have to expand. Now we see a graphic of the diffusive coefficients at 10 Celsius degrees, and with the time. We see that in the first 60 seconds, the diffusive coefficient is about 0.12 and 0.13, and then dramatically decreases to 120 seconds for a diffusive coefficient value of approximately 0.06 centimeters squared per second. This explains the behavior of this graphic, because the more they're expanding, the less space they have to expand itself in the medium. We took this difference at the as we see in the upper right part of the screen, and we see that this difference is less the more temperature is at the more temperature. We see that the pink line it's behind the 10 Celsius degrees line, that is the red line. So at higher temperatures, the difference is minor, and this means that if the difference is minor, the system is reaching the massic equilibrium faster. So yeah, it's a matter of time. In Chapman-Enskog and in the Soret equation, the diffusivity increases with the temperature, but in a zero time. The diffusivity it changes with the time, because again the molecules are moving and they're expanding in the medium. So the diffusivity in the minute number 2, it's not the same as in just when the drop is put in the medium. These also have a molecular explanation, and it's the MSD. We can see that the MSD is equal to twice times the Fickian diffusivity times the time. Well, the MSD, the mean square displacement, explains how much are the molecules moving in the system, and the MSD is directly proportional with the temperature because in molecular stages, at molecular level, the temperature is nothing else than movement of the molecules, movement of everything molecularly in the system. So we can see that in the MSD, the molecules are moving more in an initial time, in a so minimal time. These molecules are spreading more in its medium, maybe water, maybe another solution, another solvent, and this force a mass equilibrium. So we need to make new measurements at lower times, about 10 or less seconds after the drop touches the medium. This is a way to see how the diffusivity increases with temperature and how the changes of the dissolution are reflected in the diffusion coefficient. As we see in the screen, Longsworth in 1954 takes an albumin fraction in an aqueous solution and with different temperatures, 1 Celsius degree and 25 Celsius degree, calculates the diffusion coefficient value. And the higher temperature coefficient is 2 times the lower temperature coefficient diffusion coefficient value. Treat in 1213 also noticed this behavior with PCVM in 1213 with 4 different temperatures: 110 Celsius degree, 19 Celsius degree, 70 Celsius degree, and 50 Celsius degree. We see that the behavior of the graphic and behavior of the diffusion coefficient at lower times is equal to our hypothesis and equal to the Longsworth study in 1954. Well, finally, the conclusions. The conclusions of this practice are that the objectives of their practice were reached. We can also conclude that a minute is a long time to measure the diffusion coefficient because at a minute the system is going to the equilibrium. Maybe with other time distribution would be easier to calculate the diffusion coefficient. In other terms, the diffusion coefficient we know that increases directly with the temperature, and as time goes by, the diffusion coefficient decreases drastically as the system reaches the equilibrium and as the time passes by. Thank you.